July 23rd, 1983, Air Canada Flight 143, a brand new Boeing 767, climbs through 41,000 feet over Western Ontario, carrying 61 passengers, 8 crew, and exactly half the fuel the pilots believe they have. The aircraft is running on borrowed time because someone confused pounds with kilograms during Canada's transition to the metric system. In 12 minutes, both engines will quit. The jet will become a 132-ton glider with no power, no hydraulics, and 69 souls aboard. The 767 was the first wide-body designed with a digital fuel system. No mechanical gauges, just computers calculating weight in the new metric standard. But the fuel quantity processor on this aircraft was broken. So the ground crew fell back to manual calculations, dipstick readings, conversion factors, and a number written on a scrap of paper. Somewhere in that chain, someone used 1.77, the conversion for pounds per litre, when they needed 0.8, the factor for kilograms per litre. The math said full tanks. The tanks held 22,300 pounds when the flight plan required 22,300 kilograms. Captain Robert Pearson and First Officer Maurice Quintal had no reason to doubt the numbers. The paperwork matched. The ground engineer signed off. The aircraft was cleared for a routine flight from Montreal to Edmonton. But as the 767 cruised west over the forests and lakes of central Canada, the fuel gauges, blank since departure, told no lies. The tanks were draining toward empty. The engines, fed by physics instead of paperwork, would run until the last kilogram burned away. The problem began years earlier, in a policy room far from any cockpit. In 1970, Canada passed the Metric Conversion Act, a decade-long campaign to abandon pounds, gallons and miles in favour of kilograms, litres and kilometres. By the early 1980s, road signs had flipped, gas pumps read litres, and grocery scales weighed in grams. But aviation moved slower. Pilots still thought in feet and knots. Fuel trucks carried conversion charts. And on July 23rd, 1983, Air Canada Flight 143 became the country's first 767 to refuel entirely in the new system. Kilograms of jet fuel, not pounds. Which meant the refueling crew at Montreal that morning stood at the hinge of two worlds. The 769's fuel quantity processor, the digital brain that automatically converted volume to mass, was inoperative, listed as acceptable under the minimum equipment list. So the ground engineer pulled a dipstick, read the volume in the tanks, then reached for a conversion factor to calculate kilograms. He wrote 1.77 on his worksheet, the number that turns litres into pounds. The number he needed to turn litres into kilograms was 0.8. No alarm sounded. The captain signed off. The aircraft pushed back with less than half the fuel the flight plan required. The refueling began in Montreal with a dipstick measurement. The fuel quantity processor, the digital system that should have displayed litres in the cockpit, was inoperative. A known defect the airline had deferred. So the ground crew measured the fuel tanks manually, reading the depth in centimetres, then converting that to volume. They found roughly 7,700 litres already aboard. The flight plan called for 2,300 kilograms of fuel to reach Edmonton. Subtracting the 7,700 litres on board, they needed to add fuel. But the pump measured in litres, and the plan specified kilograms. The conversion factor between litres and kilograms of jet fuel is roughly 0.8. The ground engineer, however, used 1.77, the factor to convert litres to pounds, not kilograms. The captain, unfamiliar with metric, trusted the calculation. Using 1.77, the math said they had far more fuel mass than they did. They pumped what they thought was enough, and the gauges, dark and silent, offered no correction. In reality, Air Canada 143 departed Montreal with roughly 9,800 kilograms of fuel aboard. The flight plan required 22,300. They had less than half. The error was now airborne, climbing through the summer sky toward Red Lake, Ontario. But the conversion error was only half the story, because two separate safety systems were supposed to catch it, and both failed the same day. First, the minimum equipment list, the rulebook that defines what can be broken before a flight is grounded. The MEL allowed one fuel quantity processor channel to be inoperative, but not both. On Flight 143, both channels were dead, yet the aircraft was cleared for departure anyway. Second, the dripstick calculation itself required a 3-person check: ground engineer, first officer, and captain, each verifying the math independently. All three used 1.77, the pounds factor, because that's what the previous crew had written on the refueling slip. No one questioned it. No one pulled out the conversion chart. The 767 was so new that the standard procedures for metric fueling hadn't been drilled into muscle memory yet. Years later, the accident report would identify the core failure: normalization of deviance. The fuel processor had been broken for days. Manual calculations had become routine. And because nothing had gone wrong yet, each small violation of procedure, skipping the chart, trusting the previous shift's number, clearing an aircraft that should have been grounded, felt safe, until the math caught up with them at 41,000 feet. Now the error became physics. At 8:48 p.m, cruising over Red Lake, Ontario, the left engine coughed once, then quit. The low-pressure fuel pump had nothing left to draw. Captain Pearson and First Officer Quintal ran the engine failure checklist: restarting procedures, cross-feed valves, standard drill for a single engine event. But 4 minutes later, the right engine died too. The cockpit went silent. No whine of turbines, no hum of generators. The 767's screens flickered and went dark. What the crew faced next had never been simulated, never practiced, never imagined by Boeing's engineers. A 760 Afen is not designed to glide. It's a 130-ton brick optimized for powered flight, with hydraulic systems that depend on engine-driven pumps. As the turbines spooled down, hydraulic pressure bled away. The flight controls stiffened. The ram air turbine, a small emergency windmill, dropped into the slipstream and began spinning, generating just enough power to keep the rudder and elevators barely responsive. The 767 was now descending at 2,000 feet per minute, a rate that would give them roughly 20 minutes before impact with the forested wilderness below. Air traffic control heard the mayday. Flight 143, dual engine failure. We are in emergency descent. The controller's voice came back calm, procedural, asking for souls on board and fuel remaining. Pearson's reply was 3 words that rewrote the manual: fuel exhaustion, gliding. The pounds versus kilograms error. The number on that scrap of paper in Montreal had just turned a wide-body jet into the largest unpowered aircraft in civil aviation history. But here's the catch. The man in the left seat was not a typical airline captain. Robert Pearson held a commercial glider license and had logged hundreds of hours soaring unpowered sailplanes over the fields of southern Ontario. He understood energy management in a way no jet-trained pilot ever practiced: how to read descent angles by feel, how to stretch a glide by trading altitude for distance, how to judge a landing approach with no throttle to correct mistakes. It was a weekend hobby. On July 23rd, it became the only reason 69 people would survive. No airline simulator in 1983 trained pilots to fly a 700 Riemann. As a glider, the aircraft was designed with triple redundant hydraulics, backup generators, and ram air turbines that deployed if both engines failed. A scenario Boeing considered so unlikely, it barely warranted a checklist entry. Pearson had never practiced this. No one had. But he had spent years learning to feel the sink rate of a sailplane, to judge the invisible trade between airspeed and altitude, to commit to a landing spot miles away with no second chance. Those instincts were about to be tested at a scale no glider pilot had ever faced. Years later, investigators would note the improbability, a fuel miscalculation that left the jet with less than half its required load, a captain who happened to hold a glider rating. An abandoned military airstrip within gliding range, the Gimli Glider survived because 3 separate coincidences aligned in the same afternoon. Remove anyone: the hobby license, the decommissioned runway, the clear weather, and the outcome changes. Luck is not a system, but on this flight it was the only system that worked. Pearson's best option was RCAF Station Gimli, a decommissioned Royal Canadian Air Force base 70 miles southwest, with a long concrete runway he'd flown into during his military service years earlier. It was within gliding range, barely if they held altitude discipline and didn't bleed energy turning. Quintal pulled the approach charts and radioed Winnipeg Center with their intention. What neither pilot knew, what no one in air traffic control knew, was that Gimli's runway had been officially closed to aviation 2 years prior. The northern half had been left intact for emergency use, but the southern section had been turned over to the town. The southern section had become a drag racing strip. That July evening, the Winnipeg Sports Car Club was holding a race meet. Dozens of spectators lining the old taxiway, kids on bicycles weaving between parked campers, drivers revving engines at the start line. The northern half the emergency section Pearson was aiming for was supposed to be clear, but no one had erected barriers. No one had notified air traffic control that the runway was now a public recreation site, and no one on the ground had any reason to look up and expect a wide-body jet descending in silence toward them. So now the improbabilities stacked. A fuel miscalculation that left a 767 powerless over wilderness, a captain whose glider hobby gave him the skills to fly it unpowered, and an abandoned military runway just within range, which happened to be hosting a drag race at the exact moment a silent airliner was gliding toward it at 180 knots. The convergence was so unlikely that investigators would later struggle to assign probabilities. Pearson had no thrust to go around, no hydraulics for a normal flare, and no way to warn the people on the runway below that 132 tons of aluminum was about to arrive. Pearson had no engine thrust to adjust his descent, no way to add power if he came in short, no way to go around if the approach went wrong. He flew the 767 like a sailplane, trading altitude for distance. But sailplanes weigh 2,000 pounds and land at 60 knots. This was 132 tons descending at 240 knots, and the runway at Gimli was coming up fast. He needed to bleed speed without flaring too high. A mistake of seconds or 10 feet would mean a stall, a nosedive, or overshooting into the crowd. He came in high and fast, too fast for a normal landing, but the only way to guarantee he'd reach the runway. At the last moment, he pitched the nose up sharply to scrub off speed, the 767's tail nearly dragging, the stall warning horn blaring in the cockpit. The main gear hit hard. Then the nose slammed down with such force that the front landing gear, never designed for that angle of impact, collapsed instantly. The nose dug into the pavement, throwing sparks 30 feet into the air as the fuselage scraped forward on its belly. The 767 slid 1,500 feet, trailing smoke and debris, before grinding to a stop less than 100 yards from the crowd of spectators and parked campers. The drag racers scattered, families ran. But inside the cabin, the emergency slides deployed, and all 69 passengers and crew evacuated down the chutes onto the runway. Shaken, some with minor injuries from the hard landing, but alive. Not one person died. The Gimli Glider had landed among a summer festival, and the only casualty was the aircraft's nose. The Gimli Glider was not an isolated case. It was one entry in a decades-long catalogue of unit conversion disasters. In 1999, NASA's Mars Climate Orbiter burned up in the Martian atmosphere because Lockheed Martin's software output thrust in pound-force seconds, while NASA's navigation team expected Newton seconds. The $125 million probe disintegrated because no one caught the mismatch. In 1983, the same year as Flight 143, a concrete beam at a British construction site collapsed during a load test. The engineer had converted kilonewtons to pounds force incorrectly, underestimating the stress by a factor of 4. The human brain is terrible at unit vigilance, and we see numbers, not dimensions. When a calculation produces a plausible result, we accept it. When the units are familiar from yesterday's work, we don't question them. And so the error persists until it manifests as physics. An orbiter too low, a beam too weak, a fuel tank half empty at altitude. The lesson engineers drew from Gimli was this: redundancy cannot be procedural. 3 people checking the same wrong number is not redundancy. It must be structural. Different instruments, different methods, different units that force conversion at the boundary, making the error visible before it becomes irreversible. The Gimli Glider survived because 3 improbabilities converged at once. Not because any safety system caught the error before 37,000 feet. The lesson isn't that luck saves us. It's that fragile systems hide their fragility until the moment all the coincidences align in the wrong direction. Every checklist you skip, every unit you don't verify, every backup you assume will catch it. Those are bets on improbability. And improbability always collects. Engineer for failure, never rely on coincidence, rely on